For 5 million years, they were the undisputed architects of a frozen empire. The Mammoth lineage did not merely survive the Pleistocene epoch, its individual members actively engineered it. Their reigns spanned multiple continents, shaping the biology of the entire Northern Hemisphere and driving nutrient cycles on a scale that rivals modern geological forces. Yet, the story of their end is frequently reduced to a cinematic myth. Popular imagination paints a picture of a sudden overnight freeze, an apocalyptic blizzard that flash froze these towering mammals with green grass still in their mouths. The scientific reality is far more intricate, and in the context of planetary history, much more unsettling. They were not erased by a singular, sudden cataclysm. Their extinction was a slow, agonizing unraveling of an incredibly complex biological network. It was a process that stretched across millennia, with the very last isolated populations fading away in absolute silence a mere 4,000 years ago, during a time when human civilizations were already constructing great pyramids of stone. Understanding this collapse requires us to look beyond simple narratives of ice and snow. It demands that we examine the delicate margins of planetary survival. The fall of the mammoth serves as a profound case study in ecological fragility, demonstrating how minor shifts in orbital mechanics, deep ocean currents, and global atmospheric temperatures can permanently dismantle a continental ecosystem. It forces us to ask how resilient any dominant species truly is when the underlying mechanisms of their world begin to shift beneath their feet. Today, we explore our central topic, mammoths, 5 million years of reign and a final, silent end. Before we descend into the depths of this ancient timeline, please take a moment to like this video, subscribe to our channel, and leave a comment below telling us exactly where in the world and what time it is as you join us on this journey. To understand the ultimate architect of the ice, we must first look to the equator. It is a profound irony of planetary biology that the most iconic creature of the deep freeze was forged in the sweltering tropical environments of the African continent. The mammoth lineage belongs to the order Proboscidea, a diverse group of trunked mammals whose evolutionary history stretches back over 50 million years. Before we trace their path to the tundra, it is crucial to untangle the mammoth from another famous prehistoric giant, the mastodon. While popular culture often conflates the two, their evolutionary paths diverged tens of millions of years before the first true mammoth ever took a breath. Mastodons held on to an ancient, deep forest ecological niche, retaining cone-shaped teeth designed exclusively for crushing soft twigs and woodland vegetation. The mammoth lineage, however, was forced down a drastically different path by the shifting mechanics of the planet itself. The earliest recognized member of this new lineage is Mammothus subplanifrons, which appeared in what is now South Africa around 5 million years ago. During this epoch, global temperatures were slowly beginning to drop, locking up atmospheric moisture in the polar regions. This planetary-scale desiccation transformed lush African forests into vast, open savannas. For the ancestors of the mammoth, this environmental shift was a violent evolutionary filter. They were forced to leave the receding tree lines and step out into the open grasslands to survive. This transition required a radical feat of biological engineering, particularly in their digestive and anatomical architecture. The new open plains were dominated by tough, fibrous grasses, heavily fortified with microscopic crystals of silica known as phytoliths. Consuming this vegetation is equivalent to chewing on fine sandpaper. A species with traditional mammalian teeth would rapidly grind its enamel down to the nerve, resulting in starvation. The mammoth lineage survived this deadly selective pressure by developing an ingenious dental mechanism. Their molars evolved into massive, flat blocks, laced with tightly packed, parallel ridges of highly resilient enamel. Furthermore, they developed a continuous conveyor belt system of tooth replacement. As the abrasive grass wore down the front of the tooth, new dental material constantly pushed forward from the back of the jaw. By analyzing the carbon isotope signatures locked within the fossilized enamel of Mammoths subplanifrons, paleoclimatologists can read the exact moment this species shifted from a forest diet to a life on the open plains. But the story of the mammoth does not remain confined to the African continent. This brings us to a phenomenon known as adaptive radiation, a rapid evolutionary expansion where a single lineage diversifies to fill multiple ecological niches across new environments. Around 3 million years ago, shifting tectonic plates closed the oceanic gateway between North and South America. This geological event violently rerouted global ocean currents, triggering a severe cooling effect across the Northern Hemisphere. As sea levels fluctuated, land bridges emerged, creating temporary highways out of Africa. The mammoths seized this opportunity, migrating into the vast, unexploited territories of Eurasia. This migration was not a simple relocation. It was the beginning of a profound physiological transformation. As they pushed further north, the lineage splintered. We see the emergence of Mammoths meridionalis, the southern mammoth, which successfully colonized the temperate mosaic parklands of Europe and Asia. Yet Earth's climate engine was continuing to stutter. The planet was entering the early stages of the Pleistocene epoch, characterized by the rhythmic expansion and retreat of immense continental ice sheets. This leads to a deeper consequence regarding how life interacts with a destabilizing planetary climate. Biological forms are essentially thermodynamic machines, negotiating with the thermal limits of their environment. As the European and Asian continents grew progressively colder and drier, the southern mammoth faced a stark choice: adapt or perish. The evolutionary answer was Mammoths trogontherii, the steppe mammoth. This was a true giant, standing vastly taller than modern elephants, representing a biological principle known as Bergmann's rule. This rule dictates that animals in colder climates tend to evolve larger body masses, minimizing their surface area to volume ratio, and thereby dramatically reducing the loss of core body heat. The skull of the steppe mammoth also underwent a drastic architectural redesign. It became highly compressed from front to back, growing taller and uniquely domed. This was not a random mutation. It was a structural necessity to anchor the massive neck muscles required to support exceptionally long, heavy tusks. These tusks were no longer just weapons for dominance. They were becoming essential tools for manipulating a harsh, snow-covered landscape. And right here, this evolutionary sequence begins to connect with a much larger scientific question. If we view this progression through the lens of planetary biology, the mammoth lineage serves as a perfect biological sensor for Earth's descent into the ice ages. Their bodies are a physical record of cooling global temperatures. The selective pressures that shape them from the tropical African savanna through the temperate Eurasian forests and out onto the freezing, wind-blasted steppes demonstrate the immense plasticity of complex life. It shows how subtle variations in a planet's orbital mechanics can redraw the entire biological map of a hemisphere. Ultimately, the extreme selective pressures endured by the steppe mammoth laid the absolute genetic groundwork for the final, most specialized iteration of the lineage, setting the stage for the arrival of the woolly mammoth. To survive the extreme thermal crash of the late Pleistocene, the woolly mammoth had to achieve something biologically extraordinary. It had to wage a perpetual war against the laws of thermodynamics. A warm-blooded mammal operating in environments that plunge to negative 50 degrees Celsius is a walking thermodynamic anomaly. Physics dictates a relentless transfer of heat from the warm body to the freezing surrounding atmosphere. To halt this fatal energy drain and maintain a strict internal core temperature, the mammoth evolved a suite of interlocking physiological mechanisms that pushed the absolute boundaries of mammalian biological engineering. The most profound of these adaptations did not occur on the outer surface of the animal, but deep within the molecular structure of their blood. In modern elephants, and indeed most mammals, hemoglobin, the critical protein responsible for transporting oxygen, becomes highly stable at freezing temperatures. This stability is a deadly flaw in the extreme cold. It means that in the freezing extremities of an animal, such as the lower legs or the trunk, the blood binds too tightly to oxygen, refusing to release it to the surrounding tissues. This rapidly leads to cellular asphyxiation, tissue necrosis, and severe frostbite. But the mammoth lineage engineered a molecular bypass. By sequencing highly degraded ancient DNA, extracted from Siberian permafrost, modern paleogeneticists managed to isolate the specific genetic sequence for mammoth hemoglobin. In a staggering feat of molecular biology, researchers actually inserted this extinct gene into living bacteria, synthesizing real mammoth blood proteins in a laboratory to test their thermal properties. The physical results revealed 3 distinct genetic mutations that force the hemoglobin to offload oxygen with perfect efficiency, even in near-freezing environments. And right here, this biological mechanism begins to connect with a much larger scientific question. If carbon-based chemistry can be naturally reprogrammed to function perfectly at the edge of freezing, it radically expands our parameters for astrobiology. When we search for complex life on exoplanets situated on the cold, dim outer fringes of their respective habitable zones, the mammoth circulatory system provides a proven biological blueprint for how warm-blooded alien organisms might continuously oxygenate their tissues in sub-zero worlds. But internal molecular chemistry is only the first line of defense. To minimize passive heat loss, the mammoth radically altered its surface geometry. Following Allen's rule, a biological principle holding that endothermic animals in cold climates must reduce their surface area to volume ratio, the mammoth developed remarkably small ears and a short, stumpy tail compared with those of its closely related tropical elephant cousins. This physical retraction severely minimized the amount of exposed flesh vulnerable to the biting wind, sealing off the most common avenues for thermal leakage. Yet, even with optimized blood and reduced surface area, surviving the tundra required a heavy-duty physical containment barrier. The mammoth developed a highly sophisticated, 3-tiered physical insulation system. The foundation of this system was a vast subcutaneous layer of fat, measuring up to 10 centimeters thick in places. However, this was not ordinary white adipose tissue used merely for caloric storage. It was heavily enriched with brown fat. Packed with iron-rich mitochondria, brown fat serves as an active biological furnace. Through a metabolic process known as non-shivering thermogenesis, these specialized fat cells essentially burn calories to generate their own localized heat, providing a continuous, active internal thermal baseline without the need for muscle friction. Layered directly above this metabolic furnace was an incredibly dense undercoat of highly crimped, fine wool. This secondary tier functions strictly through the physics of gas confinement. By trapping a stationary boundary layer of dead air against the warm skin, it neutralized conductive heat transfer. In the natural world, trapped air is an unmatched thermal insulator, creating a thermodynamic vacuum between the animal's core and the freezing external atmosphere. Guarding this delicate undercoat was the third and final physical layer, a cascading exterior of coarse, rigid guard hairs, some extending over 90 centimeters in length. These thick hairs acted as a primary windbreaker, a physical shield against mechanical damage from ice, and a mechanism to shed accumulating snow. But this complex 3-part armor possessed a fatal vulnerability. If the dense, woolly undercoat ever became saturated with moisture, the trapped air would instantly be replaced by water. Because water conducts heat away from a body at nearly 30 times the rate of static air, a wet mammoth would suffer rapid, irreversible hypothermia. To counteract this constant environmental threat, its skin was embedded with hyperactive sebaceous glands. These glands operated continuously, pumping out massive quantities of thick, specialized biological sebum. This dense grease coated every single strand of exterior hair, rendering the mammoth profoundly waterproof. Freezing rain and melting snow simply beaded up and rolled off the outer guard hairs, leaving the vital thermal air trap underneath entirely untouched and bone dry. At a planetary scale, the meaning of this biological architecture changes entirely. The woolly mammoth was not simply surviving the cold, it was a self-contained, mobile, thermodynamic fortress, meticulously engineered to exploit an extreme environment that would instantly terminate almost any other megafauna on Earth. However, this extreme level of hyper-specialization introduces a terrifying ecological paradox. The more perfectly an organism is adapted to a singular, extreme set of planetary conditions, the more fragile it becomes when those planetary conditions inevitably begin to shift. Their ultimate weapon against the deep ice age would eventually become a fatal, suffocating liability when the global climate engine began to warm. Surviving the extreme thermal crash of the Pleistocene required more than just external insulation. It demanded an industrial-scale internal energy source. The Mammoth Steppe was vast, but it was essentially a frozen nutritional desert for much of the year. To maintain their core body temperature, a mature woolly mammoth had to consume upwards of 200 kilograms of tough, freezing, nutrient-poor vegetation every single day. Processing this staggering volume of raw material required the mammoth to evolve into a highly specialized, mobile biological reactor. The mechanical intake of this system relied on a highly advanced dental architecture, but one with a tragic built-in obsolescence. Unlike humans, who grow only 2 sets of teeth over a lifetime, mammoths utilized polyphyodonty. They possessed a sequence of 6 sets of massive, brick-like molars that slowly migrated forward along the jawline like a biological conveyor belt. As the abrasive silicates in the steppe grass ground the active tooth down to the root, it would break apart and fall out, immediately replaced by the fresh molar pushing from behind. But this evolutionary engineering had a hard mathematical limit. When the 6th and final set of molars wore down, usually when the animal reached its 60s, the hardware simply failed. Unable to crush the fibrous fuel, the mammoth would succumb to starvation. It is a stark demonstration of how biological systems are fundamentally constrained by mechanical wear, placing a hard physical ceiling on the lifespan of complex organisms, regardless of their environmental success. Once the vegetation was mechanically pulverized, it entered the mammoth's expansive hindgut fermentation system. Here, an enormous anatomical chamber known as the cecum functioned as a continuous flow fermentation bioreactor. Because mammals cannot naturally digest cellulose, the mammoth relied on a vast symbiotic microbiome of specialized bacteria and protozoa to break down the tough plant cell walls. This microbial fermentation process was highly exothermic, meaning it released significant amounts of heat as a chemical byproduct. Thus, the mammoth's digestive tract doubled as an internal radiator. The sheer volume of biomass constantly fermenting in its gut generated a continuous flow of metabolic heat, warming the blood before it circulated to the freezing extremities. But this thermodynamic engine required an uninterrupted fuel supply, and for 8 months of the year, that fuel was locked beneath a dense layer of compacted snow and ice. To access it, the mammoth required specialized heavy machinery. This is the true biological purpose of their iconic, massive tusks. While modern elephant tusks are relatively straight and used primarily for stripping bark or intraspecific combat, the tusks of the woolly mammoth were radically re-engineered by the pressures of the Ice Age. They grew into immense, spiraling curves, sometimes exceeding 3 meters in length and weighing over 40 kilograms each. The biomechanics of this curvature are a masterpiece of evolutionary structural engineering. A straight tusk used to bulldoze heavy, compacted snow would be highly susceptible to snapping at the root due to localized mechanical shear stress. The spiraling geometry of the mammoth tusk, however, perfectly distributed these mechanical force vectors. By sweeping their heads from side to side, the curved outer edges of the tusks acted like giant biological snowplows, clearing wide swathes of the steppe without placing fatal stress on the animal's skull. The structural matrix of the ivory itself, composed of rigid hydroxyapatite crystals embedded in a flexible mesh of collagen proteins, provided a tensile strength and cold weather durability that rivals modern synthetic composites. But the scientific value of these tusks extends far beyond their biomechanical function. Today, they serve as the ultimate biological flight recorders of the Pleistocene epoch. Because mammoth tusks grew continuously throughout the animal's life, they deposited a new microscopic cone of dentin every single day. By slicing these tusks open and analyzing them with high-resolution mass spectrometry, paleoclimatologists can read an astonishingly precise day-by-day diary of the animal's life. This leads to a profound consequence for our understanding of planetary history. The isotopic signatures locked within these daily growth rings record everything. Strontium isotopes reveal exact migration routes across the continent. Nitrogen and carbon isotopes track seasonal starvation events and shifts in vegetation. Oxygen isotopes provide a direct thermometer of the localized atmosphere during specific weeks of a specific year, tens of thousands of years ago. In the tusks of female mammoths, researchers can even detect the exact biochemical signatures of pregnancy and weaning, perfectly preserved in the ivory matrix. And right here, this biological logging mechanism connects with a much larger scientific question. If we ever discover the remains of extinct complex organisms on the frozen surfaces of exoplanets or rogue worlds, their physical structures will likely harbor similar temporal data logs. The mammoth tusk proves that biology is a high-fidelity recording medium, capable of capturing the stuttering mechanics of a planetary climate engine down to the molecular level. However, the sheer biological cost of growing and wielding these massive tools created a dangerous evolutionary trap. Generating hundreds of kilograms of specialized ivory and maintaining a massive hindgut bioreactor required a specific, predictable ecological baseline. The mammoth had optimized its anatomy so perfectly for the cold, silica-rich, snow-covered steppe that it lost all biological flexibility. When the orbital mechanics of the Earth eventually shifted and the climate engine began to rapidly reconfigure the vegetation of the Northern Hemisphere, these magnificent anatomical adaptations transformed from essential survival tools into catastrophic biological burdens. The Mammoth Steppe was the largest single biome in the history of the planet. At its peak, it formed a continuous, unbroken ribbon of cold weather grasslands, stretching from the Iberian Peninsula across the entirety of Eurasia, over the Bering land bridge, and deep into the North American continent. However, viewing this vast landscape merely as a natural habitat that mammoths happen to occupy is a fundamental scientific error. The Mammoth Steppe was not a naturally occurring baseline environment. It was an artificial construct. It was a biologically terraformed world, and the mammoths were its primary ecosystem engineers. To understand this, we must look at the mechanical interaction between massive bodies and fragile soils. In the absence of heavy herbivores, cold environments naturally default to low productivity states. Tundra ecosystems quickly become dominated by thick, slow-growing mosses and dark, woody shrubs. Moss acts as an exceptional thermal insulator, trapping the cold in the ground and keeping the active soil layer incredibly shallow, which prevents deeper-rooted, nutrient-rich grasses from taking hold. But a herd of woolly mammoths, each weighing up to 6 tons, functioned as a fleet of biological bulldozers. As they migrated, their massive, padded feet relentlessly trampled the encroaching moss layer. Their curved tusks ripped up woody shrubs and saplings, and their sheer physical mass churned the topsoil, essentially ploughing the earth on a continental scale. This constant, high-impact mechanical disturbance systematically suppress the moss and woody plants, allowing fast-growing, deep-rooted steppe grasses and herbaceous forbs to completely dominate the landscape. But the implications of this engineering extend far beyond local botany. In sub-zero environments, the geopolitical economy of nature, the nutrient cycle, faces a fatal bottleneck. In warm climates, dead plant matter rots quickly, returning nitrogen and phosphorus to the soil via bacterial decomposition. In the freezing Pleistocene, this bacterial decay practically halted. Dead vegetation simply froze in place, locking up vital nutrients in a chemical vault. The mammoth bypassed this geochemical freeze. By consuming hundreds of kilograms of vegetation daily, they essentially transferred the slow, external decomposition process into the hot biological reactors in their stomachs, operating continuously at approximately 37 degrees Celsius. A single herd would process thousands of tons of locked biomass, rapidly fermenting it, and then distributing highly concentrated, biologically available nitrogen and phosphorus back onto the chilled soil through their dung and urine. They were a mobile, rapid-fire fertilization grid, keeping the biological economy of the steppe circulating at high speeds, despite the freezing temperatures. This leads to a deeper consequence at a planetary scale. The botanical shift forced by the mammoths altered the thermodynamic equilibrium of the Earth itself. Dark mosses and boreal coniferous forests absorb a tremendous amount of solar radiation, converting light into thermal energy and warming the surrounding air. In contrast, the dry, pale grasses of the Mammoth Steppe possessed a high albedo, a high capacity to reflect incoming solar radiation back out into space. By aggressively maintaining these reflective grasslands and destroying dark, heat-absorbing vegetation, the mammoths were actively refrigerating the Northern Hemisphere. They were preventing the permafrost beneath their feet from thawing. And right here, this ecological feedback loop begins to connect with a much larger question. When astrobiologists model the long-term stability of habitable exoplanets, they often focus strictly on atmospheric chemistry and the host star's output. The Mammoth Steppe proves that complex biology is not merely a passive passenger on a planet. It is a primary driver of planetary climate mechanics. A single keystone species can grip the global thermostat. If this is true, it suggests that the longevity of a habitable biosphere, and by extension, the window for advanced civilizations to emerge, might be highly dependent on the survival of its largest biological engineers. Removing a central node does not just change the local scenery, it can trigger a planet-wide thermodynamic cascade. Because of this intense engineering, the Mammoth Steppe supported an astounding density of biomass that defies modern comparisons. It was the frozen equivalent of the African Serengeti, but this was not a chaotic free-for-all. It was a highly organized system governed by strict niche partitioning. Woolly rhinos, acting as secondary engineers, specialized in breaking down the toughest, woody vegetation that even mammoths avoided. Massive herds of steppe bison grazed the mid-level grasses, while ancient wild horses cropped the lowest shoots down to the soil. Because they compartmentalized the resources, these mega herbivores coexisted in numbers staggering to modern ecology, converting poor quality solar energy into millions of tons of high-density animal protein. This hyper-abundant energy transfer inevitably attracted a terrifying tier of apex predators. The steppe was patrolled by cave lions, a species up to 20% larger than modern African lions, perfectly adapted to hunting in the snow. Packs of direwolves coordinated to separate weak bison from the herds, while the colossal short-faced bear, standing over 3 meters tall, used its immense size to dominate kill sites and scavenge frozen carcasses. It was a fiercely kinetic, high-energy biological network. Yet, for all its continental scale and raw power, this entire biome was fundamentally fragile. The intricate web of the Mammoth Steppe, the nutrient cycling, the reflective albedo, the staggering predator-prey dynamics, was entirely suspended on the continuous mechanical and chemical labor of the mammoths. They were the load-bearing pillars of the Pleistocene world. If you remove the engineer, the moss returns, the ground warms, the nutrients lock away, and the entire continent collapses into a silent, boggy wasteland. And as the orbital cycles of the Earth began to shift, this system was about to face a stress test it could not survive. The expansion of the mammoth lineage into North America is often misunderstood as a simple, heroic march across a frozen ocean. The reality requires us to look at Earth as a closed hydrological engine. During the Pleistocene glaciations, millions of cubic kilometers of ocean water evaporated into the atmosphere, fell as snow over the poles, and simply never melted. This continuous atmospheric theft locked the Earth's liquid water into continental ice sheets over 3 kilometers thick. The global sea level plummeted by a staggering 120 meters. The Bering land bridge was not made of ice. It was the exposed floor of the Bering Sea. This newly exposed territory, known as Beringia, was not a narrow pathway. It was a massive, continuous landmass spanning over 1,000 kilometers wide, effectively welding Eurasia and North America into a single supercontinent. But the issue does not stop at simple geography. Beringia was a high-latitude thermal anomaly. Because the surrounding ocean currents were severed and reorganized, the region experienced extreme atmospheric aridity, preventing the massive glacier formation seen elsewhere at similar latitudes. It became a dry, freezing extension of the Mammoth Steppe, an open highway for biological expansion. At a planetary scale, the implications of this mechanism alter how we view habitability and the evolution of complex life. When astrobiologists scan exoplanets, the presence of stable liquid water is the primary metric. But the Beringia mechanism suggests that a perfectly stable climate might actually induce evolutionary stagnation. It is the rhythmic instability of a planet, the violent transfer of mass from the oceans to the continents, that forces isolated biomes to collide. If a habitable world lacks these extreme hydrological cycles, its biological networks might never cross-pollinate, permanently capping the complexity of its biosphere. Conversely, if the freeze is too severe, the entire planet enters a terminal snowball Earth state. The mammoth expansion across Beringia occurred on a razor-thin margin of planetary physics, a delicate, oscillating pulse that drives macroevolution rather than extinguishing it. As the ancestral mammoths pushed across Beringia and funneled down into the lower latitudes of North America, they encountered a radically different thermodynamic landscape. The deep freeze of the Siberian steppe gave way to the temperate savannas and scrublands of what is now the United States and Mexico. The ultimate cold weather machine was suddenly subjected to the threat of catastrophic overheating. To survive this new planetary zone, the lineage underwent a rapid morphological divergence, resulting in the Columbian mammoth. The Columbian mammoth, Mammothus columbi, represents a stunning reversal of their previous evolutionary trajectory. They shed the dense, crimped undercoat and the massive brown fat reserves that defined their northern cousins. Relieved of the extreme metabolic burden of generating internal heat, they redirected that biological energy into pure structural growth. They grew significantly larger, towering up to 4 meters at the shoulder and weighing over 10 tons. Their dental architecture adapted to a broader, more diverse diet, shifting from purely abrasive steppe grasses to include a higher percentage of leaves, fruits, and temperate vegetation. They became the undisputed masters of the American South. And right here, modern genomic data introduces a profound complication that completely rewrites classical evolutionary theory. For decades, paleontologists viewed the woolly mammoth and the Columbian mammoth as two distinct, isolated branches on a clean Darwinian tree. But the extraction of highly degraded nuclear DNA from fossils found in the geographical overlap zones of North America revealed a stunning reality. The evolutionary tree is not a tree at all. it is a tangled web. As the North American ice sheets violently advanced and retreated over millennia, the habitats of the woolly and Columbian mammoths continuously expanded and contracted, forcing the two species into overlapping territories. The genetic sequencing proves that these two distinct animals interbred extensively, creating vast populations of hybrid mammoths. This process, known as reticulate evolution, proves that the boundaries between species are entirely porous under the extreme stress of climate shifts. They were essentially exchanging biological software in real time, effectively swapping cold-weather genetic codes for large body mechanics to survive the chaotic oscillations of the Pleistocene climate. This leads to a deeper consequence regarding the survival of complex systems and the eventual fate of technological civilizations. The ability to fluidly exchange genetic data across species lines provided a massive buffer against extinction. It was a biological failsafe against a rapidly changing planet. But it also demonstrates that when the physical parameters of a world shift faster than the genetic code can rewrite itself, even the most dominant, highly engineered systems face a terminal collapse. The American continent provided a vast new empire for the mammoth lineage, but it was an empire built on the shifting tectonic and climatic fault lines of an inherently unstable world, setting the stage for a dramatic ecological reckoning. The retreat of the continental ice sheets triggered a planetary-scale geographic restructuring. As billions of tons of glacial fresh water poured back into the oceans, global sea levels surged, violently redrawing the maps of the Northern Hemisphere. Peninsulas became islands, and high mountain ridges were suddenly surrounded by deep marine trenches. For the mammoth populations caught on these newly formed isolated landmasses, the very physical attributes that had guaranteed their survival now became a catastrophic biological liability. They were abruptly trapped in closed ecological systems with finite, strictly bounded resource pools. To understand their survival strategy, we must examine the biological economy of mass. On a vast continental steppe, massive size is a thermodynamic advantage, providing thermal inertia against the cold and immunity to apex predators. But biological mass requires immense caloric fuel. A mature Columbian mammoth required hundreds of kilograms of vegetation daily. When confined to an island with limited square footage and no possibility of seasonal migration, this metabolic demand is an absolute death sentence. The environment imposes a brutal evolutionary filter: shrink or starve. This process is governed by an evolutionary mechanism known as Foster's rule, which dictates that large mammals isolated on islands rapidly evolve into miniature versions of their continental ancestors to align with the depleted carrying capacity of the land. The most striking evidence of this physiological adaptation occurred off the coast of California on the Channel Islands. Here, isolated populations of the towering Columbian mammoth underwent a radical process of evolutionary downscaling, transforming into an entirely new species, the pygmy mammoth. Within just a few tens of thousands of years, a mere blink in geological time, these animals shrank from 10-ton giants to the size of a modern draft horse, weighing less than a single metric ton. This was not merely a proportional reduction, it was a complete anatomical re-engineering forced by the rigid constraints of geography. Their skeletal architecture was drastically modified to navigate the steep, mountainous topography of the islands, a stark contrast to the flat, open plains of the continental interior. Their lower leg bones became significantly shorter and thicker, lowering their center of gravity to prevent fatal falls on rocky inclines. Their dental structure altered to process the specific, limited local flora. They essentially traded the biomechanical advantages of extreme size for the metabolic efficiency necessary to survive in a heavily restricted energetic environment. But the extremes of this phenomenon were pushed even further in the Mediterranean Sea. On the island of Crete, an older lineage of the mammoth family became completely isolated. The resulting species represents the absolute physical limit of proboscidey and dwarfism. These adult mammoths shrank to roughly 1 meter at the shoulder, essentially the size of a modern baby elephant, weighing a mere 300 kilograms. Paleogeneticists studying these extreme dwarfs face a significant scientific debate regarding the speed of this genetic rewriting. The mutation rates required to achieve such a drastic physical reduction challenge our classical models of gradual Darwinian evolution. It suggests that under extreme environmental compression, epigenetic triggers can rapidly suppress growth hormones and completely rewrite a species' physical blueprint in a fraction of the expected time. However, this rapid biological downscaling comes with a hidden fatal cost: severe genetic bottlenecks. Because the island can only support a small number of individuals, the population loses its genetic diversity. Inbreeding becomes unavoidable, leading to the rapid accumulation of deleterious genetic mutations. The dwarfs survive starvation by shrinking, but their immune systems and adaptability become incredibly fragile. They are perfectly adapted to their isolated prison, but completely defenseless against any sudden introduction of a new pathogen or a rapid shift in local climate. And right here, this biological mechanism begins to connect with a much larger question. If we view an island not just as a piece of land, but as a rigidly closed thermodynamic system, its meaning changes entirely. An island is a microplanet. It is a finite sphere of resources suspended in an impassable medium. The evolutionary response of the mammoth, radically downscaling its physical footprint and metabolic demands to match the carrying capacity of its environment, provides a profound data point for astrobiology and the study of civilizational longevity. When astrophysicists discuss the Fermi paradox and the Great Filter, they are fundamentally talking about resource exhaustion in closed systems. Earth itself is simply a large island suspended in the lethal vacuum of deep space. If a technologically advanced civilization expands its energy consumption beyond the planetary carrying capacity, it faces the exact same thermodynamic wall that confronted the island mammoths. The biological success and ultimate fragility of the pygmy mammoth proves that survival in a closed system requires a radical, structural reduction in resource consumption. If a species or a civilization refuses to adapt to the absolute physical limits of its isolated environment, it will simply consume its host system until total systemic collapse. In this light, the fossilized remains of dwarf mammoths are not just biological curiosities, they are ancient, proven models for the brutal mathematics of long-term planetary survival. The mammoth was the undisputed pinnacle of Pleistocene biological engineering, a self-contained thermodynamic fortress perfectly synchronized with the Ice Age. But as the epoch wore on, this biological masterpiece was forced into a collision with a completely alien evolutionary strategy. Across the freezing steppes of Eurasia, and eventually the plains of North America, mammoths encountered various species of hominins. This was not a standard ecological rivalry between two apex predators. It was a clash of fundamental planetary paradigms. On one side was millions of years of slow genetic adaptation. On the other was the explosive, unconstrained force of technological transmission. The popular image of prehistoric humans interacting with mammoths is often reduced to chaotic, desperate scrambles, with primitive hunters blindly chasing terrified herds off cliffs. The scientific reality, unearthed from dozens of meticulously excavated kill sites, reveals a chillingly calculated, high-risk economic exchange. To understand this dynamic, Paleolithic archaeologists rely on taphonomy, the exact science of how organisms decay and become fossilized. When researchers discover a mammoth skeleton intertwined with stone tools, they do not simply assume a hunt occurred. They must reconstruct the exact sequence of death using scanning electron microscopes. At a microscopic level, bone damage acts as a high-fidelity recording of prehistoric violence. When a direwolf or a cave lion bites into a bone, their rounded enamel teeth leave distinct U-shaped grooves. But when a hominin slices through muscle and tendon using a napped flint blade, the razor-sharp microscopic edge leaves a jagged V-shaped striation. By mapping the cross-sections of these overlapping marks, archaeologists can read the timeline of a carcass. If carnivore marks lie beneath stone tool cuts, humans were merely scavenging a natural death. But at sites across Europe and the Americas, the V-shaped stone cuts are found directly on the bone beneath the deepest muscle attachments, overlaid by carnivore marks. This proves beyond a doubt that humans were the primary aggressors, orchestrating the kill and executing a systematic butchery before the natural scavengers even arrived. In Pleistocene Europe, interactions between Neanderthals and mammoths were largely governed by the brutal physics of close-quarters combat. Neanderthals did not possess complex projectile technology. Their weapon systems consisted of heavy, thick wooden spears tipped with massive stone points, designed strictly for thrusting. Taking down a multi-ton mammoth with a thrusting spear required an astonishing amount of biomechanical force and an exact, terrifying proximity to the animal. The archaeological record of Neanderthal skeletons reveals a staggering frequency of healed bone fractures, primarily in the head, neck, and upper body. Statistically, their observed trauma profiles are nearly identical to those of modern professional rodeo riders. They were engaging in a highly dangerous thermodynamic gamble, risking massive physical destruction for the unparalleled caloric payload of a single mammoth. But the dynamics shifted dramatically when modern humans expanded into North America. Here, the Clovis culture introduced a revolution in applied physics that fundamentally tipped the balance of power. They utilized the atlatl, a specialized wooden lever that hooked onto the end of a flexible spear. By artificially extending the length of the human arm, the atlatl multiplied the angular momentum of a throw. It allowed a human hunter to launch a projectile at tremendous velocities, effectively weaponizing kinetic energy from a safe distance. The projectile itself, known as the Clovis point, was a masterpiece of aerodynamic and lethal design. It was fluted, featuring a concave groove chipped out of its base, which allowed it to be securely lashed to a wooden shaft and absorb the immense shock of impacting a mammoth's thick hide without shattering. These weapons were not designed to simply bleed an animal out. They were engineered to penetrate the thick layers of brown fat and sever major arteries or puncture lungs. At sites like the Naco Mammoth Kill in Arizona, archaeologists found 8 Clovis points embedded in the ribs and vertebrae of a single Columbian mammoth. And right here, this technological leap begins to connect with a much larger question regarding the longevity of intelligent life. For the entirety of Earth's history, a species' capacity to harvest energy from its environment was strictly limited by its biology. An animal could only kill what its own jaw strength, muscle mass, and running speed allowed. But the Clovis point and the atlatl represented a profound decoupling from biological limits. Hominins were no longer constrained by their physical bodies. They could scale their lethality through technology. If this decoupling is a universal step for all emerging intelligent life across the cosmos, it also introduces a terrifying vulnerability. The Mammoth Kill site is not just a prehistoric crime scene, it is the earliest recorded shadow of what astrobiologists call the Great Filter. When a technological species outpaces the biological carrying capacity of its environment, it begins to rapidly liquidate the ecological capital of its planet. The human mastery of external ballistics meant that the mammoth, despite its 5 million years of genetic optimization, was instantly rendered obsolete. It suggests that once a species crosses the threshold of applied technology, the primary threat to planetary stability is no longer orbital cycles or ice sheets, but the unconstrained appetite of the intelligent species itself. The interaction between Paleolithic humans and the woolly mammoth was not limited to the fleeting violence of the hunt. Once the animal was brought down, the relationship transformed from predatory to industrial. On the freezing, wind-scoured plains of the Eurasian Mammoth Steppe, basic survival resources like timber were virtually non-existent. In response, early humans did something unprecedented in the history of life on Earth. They did not just eat the mammoth, they repurposed its entire biological architecture, treating the mega herbivore not as an animal, but as a heavily concentrated deposit of raw planetary resources. This industrialization of biology is most vividly preserved in the archaeological record of the Ukrainian river valleys, specifically at sites like Mammoths. Here, researchers have excavated complex, semi-subterranean settlements constructed entirely from mammoth skeletons. These were not random piles of bone. They were mathematically precise feats of bioengineering. The foundation rings were built using interlocking mammoth mandibles, specifically chosen for their weight and geometry. The structural walls were framed with heavy femur and humerus bones, while massive curved tusks were deliberately interlocked at the top to serve as load-bearing roof arches, which were then draped with thick mammoth hides. A single dwelling required the skeletal remains of up to 100 individual mammoths. Early humans had effectively replaced geological building materials with biological ones, harvesting the structural integrity of the mammoth to construct a synthetic microclimate against the Ice Age. But the exploitation went deeper than architecture. In a landscape devoid of wood, fire requires an alternative fuel. Humans discovered that mammoth bones, when still saturated with rich, spongy marrow and heavy brown fat, act as highly efficient, slow-burning thermal batteries. Hearth sites found within these bone huts contain massive concentrations of charred mammoth bone. This represents a profound thermodynamic shift. Humans were essentially mining the solar energy that the mammoth had spent its lifetime harvesting from the steppe grasses, using the animal's highly concentrated fat reserves to artificially heat their local environment. It is the absolute earliest iteration of fossil fuel extraction, a species learning to burn concentrated biological carbon to defy the thermal limits of their world. However, architecture and thermal engineering only tell part of the story. To understand exactly how deeply the human biological machine relied on the mammoth, we must look away from the physical artifacts and peer directly into the atomic structure of ancient human bones. This brings us to the science of stable isotope analysis. You are, quite literally, what you eat. As an organism consumes food, the specific chemical isotopes of that food are permanently incorporated into the collagen matrix of their growing bones. By placing fragments of Paleolithic human bone into a mass spectrometer and vaporizing them, scientists can count the exact ratio of specific atomic isotopes, freezing the human diet in time. The most critical marker is nitrogen-15. In any ecological network, heavier isotopes bioaccumulate as you move up the trophic levels. Plants absorb standard nitrogen-14 from the soil. When an herbivore eats the plant, it excretes the lighter isotopes but retains the heavier nitrogen-15 in its tissues. When a carnivore eats the herbivore, the concentration of nitrogen-15 spikes even higher. It is a chemical ladder of planetary consumption. When researchers analyzed the bone collagen of modern humans living in Europe during the late Pleistocene, the isotope ratios returned a staggering result. The nitrogen-15 levels in these human bones were astronomical. They completely bypassed the levels seen in specialized apex predators like the saber-toothed cat or the cave lion. The atomic data proves that these early humans were not opportunistic omnivores, occasionally scavenging a dead mammoth. They were hypercarnivores, resting heavily on the absolute apex of the food web, deriving an immense percentage of their bodily protein directly from mammoth meat. And right here, this chemical signature connects to a much larger question regarding the detection of advanced life in the universe. Isotope fractionation is not just an earthly phenomenon, it is a universal law of chemistry. If we ever discover the fossilized remains of an extinct civilization on a distant exoplanet, we will not need to find their written history to understand their economy. We will simply read their rise and fall through the isotopic ratios locked in their skeletons. The unnatural buildup of specific heavy isotopes in a species' physical structure is the ultimate, unerasable biosignature of aggressive planetary exploitation. But for the humans of the Pleistocene, this isotopic dominance reveals a terrifying systemic vulnerability. By locking their entire economic, architectural, and caloric survival to a single, slow-reproducing mega-herbivore, they created an incredibly brittle existence. They hyper-specialized their technology and their biology around the mammoth. If this central biological pillar were to waver, the entire human architecture, their heating networks, and their caloric foundation would face simultaneous collapse. This dynamic provides a chilling historical model for the Great Filter. Whenever a technologically capable species aggressively optimizes its civilization around the extraction of a single, finite planetary resource, it achieves spectacular short-term success, while simultaneously setting a ticking clock on its own existence. The human mastery of mammoth exploitation was an unparalleled triumph of adaptability, but it bound the fate of the hominin directly to the fate of the ice, and the ice was about to end. The ultimate fate of the mammoth was not decided on the frozen plains of Siberia, but in the silent gravitational mechanics of the solar system. To understand the collapse of the Pleistocene epoch, we must look away from the Earth and observe the planet as a celestial object interacting with the gravitational pull of Jupiter, Saturn, and the Sun. The ice ages were not permanent, static environments. They were the direct result of a cosmic clockwork known as Milankovitch cycles. These are long-term, rhythmic variations in the orbital geometry of our planet, and they govern the master thermostat of the Earth. There are three primary mechanisms at play. First is eccentricity, the gradual stretching of Earth's orbit from a perfect circle into an elongated ellipse over a cycle of roughly 100,000 years. Second is obliquity, a 40,000-year cycle where the axial tilt of the planet shifts back and forth, altering the severity of the seasons. Third is precession, a 26,000-year wobble of the rotational axis, much like a slowing spinning top. Individually, these orbital variations exert a minor influence on the global climate. But when these three cycles align perfectly, in mathematical terms, to maximize the amount of solar radiation hitting the Northern Hemisphere during the summer months, the planetary climate engine reaches a violent tipping point. Around 15,000 years ago, this precise cosmic alignment occurred. The northern latitudes began to receive a massive influx of solar energy. The immense continental ice sheets, which had locked up millions of cubic kilometers of water, began to disintegrate. But the issue does not stop at a simple, gradual warming of the atmosphere. The planetary climate is a highly non-linear, chaotic system. As the ice melted, it triggered a catastrophic feedback loop in the global hydrological engine. Billions of tons of glacial fresh water poured rapidly into the North Atlantic. This sudden influx of buoyant, cold fresh water effectively acted as a geological dam, shutting down the density-driven ocean currents that circulate heat around the globe. This shutdown triggered an event known as the Younger Dryas, a chaotic climate anomaly where, in the midst of global warming, the Northern Hemisphere violently snapped back into a deep, extreme freeze in a matter of decades. This stuttering climate engine subjected the biosphere to wild, unpredictable thermal oscillations. For the mammoth, a creature perfectly engineered for thousands of years of absolute climatic stability, this chaos was a biological death sentence. The most lethal element of this climate shift was not the temperature itself, but the radical alteration of the planetary moisture cycle. During the height of the Ice Age, the Mammoth Steppe was incredibly cold, but fundamentally dry, resulting in a thin, manageable layer of powdery snow. But as the oceans warmed and evaporated, massive amounts of moisture were pumped into the atmosphere. When this moisture moved over the continents, it fell as heavy, deep, wet snow. More devastatingly, the chaotic temperature fluctuations caused freezing rain. This created thick, impenetrable crusts of solid ice over the steppe grasses. The biomechanical design of the mammoth tusk was engineered to bulldoze dry powder. It was utterly useless against a continuous sheet of solid ice. Starvation swept across the continent, not because the food had disappeared, but because it was suddenly locked beneath an impenetrable hydrological barrier. This leads to a deeper consequence regarding the survival of specialized biological networks. As the soil temperature rose and the moisture increased, the delicate botanical balance of the Mammoth Steppe shattered. The long-dormant bacteria in the soil awakened, aggressively decomposing the stored organic matter and releasing immense quantities of methane and carbon dioxide into the atmosphere, further accelerating the planetary warming. The dry, high-albedo steppe grasses, which the mammoths relied on, were rapidly outcompeted by encroaching bogs, toxic mosses, and dark, spreading taiga forests. The continent-spanning Mammoth Steppe fragmented into isolated, shrinking islands of viable habitat. The ultimate ecosystem engineers were rapidly losing their ability to terraform their own world. And right here, this geological mechanism begins to connect with a much larger question in astrobiology. When we model the habitability of distant exoplanets, we often assume that a perfectly stable orbit is the ideal condition for the proliferation of life. However, the Milankovitch cycles present a terrifying cosmic paradox. Without orbital variations, a planet might permanently lock into a static climate, stalling evolutionary pressure and preventing the emergence of complex intelligence. The gentle orbital wobble is the very engine that forces biological innovation. But this same mechanism acts as an inevitable, relentless great filter. The orbital variations that drive evolution eventually cross critical thresholds, triggering rapid planetary transformations that wipe out the highly specialized apex species they helped create. If this celestial dynamic holds true across the cosmos, it suggests that any technologically advanced civilization emerging during a stable interglacial period is building its entire existence on a temporary gravitational anomaly. The fall of the Mammoth Steppe is a stark demonstration that no biological empire, no matter how vast or perfectly adapted, can outlast the relentless, uncaring mathematics of planetary orbital mechanics. The disappearance of the mammoth is not merely a paleontological curiosity. It is a highly complex murder mystery written directly into the geological strata of the planet. For decades, the scientific community has been deadlocked in a fierce, multi-dimensional debate over the primary mechanism of this mass extinction. We are looking at a planetary-scale ecological collapse, and attempting to attribute it to a single, isolated variable is a fundamental underestimation of biological complexity. The debate essentially forces us to weigh the biological constraints of a species against the overwhelming forces of atmospheric physics and technological predation. Let us first examine the overkill hypothesis, frequently referred to in academic circles as the Blitzkrieg model. This framework is built entirely on the ruthless, unforgiving mathematics of population dynamics. Mammoths, much like modern elephants, were bound by an extremely slow reproductive cycle. A 22-month gestation period, followed by several years of intensive maternal care, meant that a mammoth population could only expand its numbers by a fractional percentage each year. When technologically armed human hunters, equipped with projectile weapons and organized pack tactics, rapidly expanded across the Americas and Eurasia, they introduced an entirely new mortality vector. The mathematical models driving the overkill hypothesis demonstrate that human hunters did not need to slaughter millions of animals overnight. They merely needed to elevate the annual mortality rate a few percentage points above the mammoth replacement rate. Once that mathematical threshold was crossed, the species was locked into an inescapable terminal decline. mathematically doomed to zero regardless of the surrounding climate. But the issue does not stop at simple hunting algorithms. Critics of the overkill model point to a glaring anomaly in the fossil record. Hominins and mammoths had coexisted across the Eurasian continent for tens of thousands of years before the extinction event. If human technology was the sole driver, the collapse should have registered much earlier in the geological timeline. This brings us to the climate-driven hypothesis, heavily supported by high-resolution atmospheric data carefully extracted from Greenland ice cores. These frozen time capsules reveal that the termination of the Pleistocene was not a gentle, gradual warming. It was a series of violent, chaotic thermal oscillations that severely destabilized the global hydrological engine. This climate instability triggered a catastrophic botanical reorganization across the Northern Hemisphere. The dry, highly nutritious Mammoth Steppe was rapidly dismantled. In its place, encroaching boreal forests, toxic birch shrubs, and deep, waterlogged peat bogs consumed the landscape. The mammoth possessed a highly specialized hindgut fermentation system, biologically engineered to process dry, abrasive silicates. It simply could not extract sufficient caloric energy from this newly emerging flora, nor could its massive biomechanical frame navigate the sinking, thawing mud of the expanding wetlands. Under this model, the mammoths were not primarily hunted to extinction. They were fundamentally starved and geographically displaced by a shifting planetary climate engine. To understand the absolute boundaries of this scientific debate, we must also examine the more controversial models that attempt to explain the suddenness of the collapse. The hyperdisease hypothesis suggests that expanding human populations and their domesticated dogs introduced novel, lethal pathogens across the land bridges. This Paleolithic pandemic would have swept through immunologically defenseless megafauna populations, much like historical plagues devastated isolated human societies. Furthermore, the Younger Dryas impact hypothesis posits an extraterrestrial trigger. Proponents of this model point to microscopic nanodiamonds and sudden spikes in platinum concentrations found in specific sedimentary layers, arguing that a fragmented comet struck the North American ice sheet, triggering a sudden, catastrophic deep freeze and massive wildfires. While these models struggle to achieve broad consensus due to a lack of universal, replicable physical evidence across all global extinction sites, they highlight the extreme difficulty of retroactively diagnosing the failure of a global biosphere. Today, the modern scientific consensus is converging on a much more terrifying, synthesized framework known as the synergistic extinction model. This model posits that the mammoth was caught in a deadly, compounding cascade of critical failures. The shifting orbital mechanics of the Earth altered the climate, which physically dismantled the continental steppe. This vast geographic fracturing forced the surviving mammoth populations to retreat into small, disconnected ecological islands known as refugia. Once trapped in these shrinking geographic pockets, their slow reproductive mathematics became an inescapable trap. In a vast, unbroken continent, a herd can simply migrate away from aggressive hunting pressure. In a shrinking refugium, they are entirely pinned against the edges of their degrading habitat. Human hunters acted as the final apex stressor in these enclosed systems. It was a devastating 1-2 punch. Planetary climate change built the ecological prison, and humanity systematically executed the prisoners. And right here, this multidimensional debate connects with a much larger question regarding the architecture of the Great Filter and the longevity of technological civilizations. The synergistic collapse of the mammoth demonstrates a universal law of complex systems. They rarely fail from a single, isolated shock. They unravel when multiple, independent stress vectors intersect and compound simultaneously. A changing environment degrades the baseline stability of a system, stripping away its natural margins of error, while an aggressive, extractive element applies localized, unsustainable pressure. If we project this mechanism onto the lifespan of advanced civilizations across the cosmos, the implication is stark. A civilization might possess the engineering to survive a shifting planetary climate, and it might possess the social architecture to survive its own technological infancy. But when both variables destabilize simultaneously, when environmental degradation intersects with massive resource extraction, the resulting collapse is entirely non-linear and incredibly rapid. The extinction of the mammoth serves as an ancient, earthly blueprint for how complex planetary networks unravel, serving as a permanent warning that the universe is profoundly unforgiving to any system that consumes its own margins of survival. By the time the global climate engine stabilized into the current Holocene epoch, the vast, unbroken continental empire of the mammoth had been completely erased. Yet, the lineage did not immediately vanish from the Earth. As the massive ice sheets violently melted and global sea levels surged by over 100 meters, the highest elevations of the former Beringian land bridge were sheared off from the mainland. These rising waters created isolated geographic fragments, effectively trapping the surviving mammoth herds in absolute isolation. The two most prominent of these final sanctuaries were St. Paul Island in the Bering Sea and Wrangel Island in the remote Arctic Ocean. These islands serve as a pristine, naturally occurring laboratory for studying the absolute limits of biological endurance in rigidly closed systems. On St. Paul Island, the extinction was driven by a brutal, inescapable physical constraint: the exhaustion of a fundamental chemical solvent. Mammoths require massive amounts of fresh water to process their heavy, fibrous diets. On oceanic islands, fresh water does not exist in vast subterranean aquifers. It floats as a delicate, shallow lens on top of the heavier, denser saltwater beneath the landmass. As global warming continued to raise the sea level, the physical footprint of St. Paul Island shrank relentlessly. This geographic compression squeezed the freshwater lens, forcing the trapped mammoths to cluster entirely around a few dwindling crater lakes. The resulting ecological dynamic was catastrophic. The immense physical weight and constant foraging of the concentrated mammoths completely stripped the vegetation surrounding the lakes. Without the root systems to hold the soil, severe erosion collapsed the lake banks, and the lack of plant cover vastly accelerated the evaporation of the remaining surface water. The animals were essentially accelerating the destruction of their own life support system through the sheer biological necessity of their existence. By approximately 5,600 years ago, the freshwater lens failed completely, and the St. Paul population collapsed in a localized terminal drought. But the issue does not stop at simple hydrological limits. If we view the St. Paul collapse through a broader lens, it provides a terrifyingly exact micromodel for planetary resource exhaustion. When astrophysicists study the Fermi paradox and the potential lifespan of technological civilizations, the primary threat vector is often the rapid depletion of finite planetary resources. The St. Paul mammoths demonstrate that when a highly consumptive entity is trapped in an enclosed, shrinking environment, its natural biological or technological drives will often outpace the regenerative capacity of the system. The end comes not from an external predator, but from the mathematical certainty of systemic consumption. The story of Wrangel Island, however, reveals an even more insidious mechanism of extinction. The mammoths trapped on this remote Arctic outpost managed to survive significantly longer, enduring until roughly 4,000 years ago. To put this immense timeline into perspective, while the absolute last woolly mammoths were foraging in the Arctic snow, human civilizations were already casting bronze, the Sumerians had invented written language, and the Great Pyramid of Giza was being constructed in the Egyptian desert. This stark temporal overlap forces us to realize that the extinction of the mammoth is not an event of deep geological antiquity, but a contemporary shadow looming over the dawn of human history. Despite their incredible temporal endurance, the Wrangel Island mammoths were not thriving. They were succumbing to a silent, invisible killer encoded directly into their DNA. When a population is abruptly reduced to a few hundred individuals and permanently cut off from the mainland, it enters a severe genetic bottleneck. In a massive, continent-spanning population, the fundamental engine of evolution, natural selection, operates flawlessly. If an animal is born with a deleterious genetic mutation, it is less likely to survive and reproduce, effectively purging the bad code from the global gene pool. But in a hyper-isolated, tiny population, the mathematics of survival completely invert. The gene pool becomes so shallow that inbreeding is unavoidable. Natural selection loses its mechanical grip, and a phenomenon known as random genetic drift takes absolute control. Bad mutations are no longer purged, they are randomly passed down and eventually become fixed within the entire population. Paleogeneticists have successfully sequenced the complete genome of the final Wrangel mammoths and compared it to their mainland ancestors, revealing a terrifying biological phenomenon known as mutational meltdown. The genomic data reads like a blueprint for a collapsing biological fortress. The Wrangel mammoths suffered massive deletions in the genes responsible for olfactory receptors. They were rapidly losing the ability to smell, severely crippling their capacity to forage for specific flora beneath the snow and rendering them unable to detect complex pheromones required for synchronized mating. Furthermore, researchers identified a critical mutation in a specific gene known as FOXQ1. This gene is the primary architect of the mammoth's most crucial thermodynamic defense, the rigid, highly structured outer guard hairs. Because of this mutation, the final mammoths possessed hair that was physically weak, entirely translucent, and stripped of its weather-resistant properties. The biological armor that had allowed them to conquer the Ice Age was physically disintegrating from the inside out. And precisely here, this genetic decay connects with a profound concept regarding the longevity of isolated systems across the universe. Whether it is a biological species trapped on a remote ocean island, or a technological civilization permanently confined to a single solar system, isolation breeds irreversible entropy. Without the continuous exchange of new information, whether that is fresh genetic code or novel technological paradigms, errors inevitably accumulate. The Great Filter might not always manifest as a sudden, violent cataclysm. The final silence of the Wrangel mammoths proves that the end of an empire can occur through the slow, mathematical accumulation of internal errors, a gradual mutational meltdown that leaves the system so fragile that a single harsh winter is enough to extinguish the last remaining spark of a 5 million year dynasty. In the standard thermodynamic cycle of the biosphere, death is merely a rapid transfer of energy. Taphonomy, the precise science of how organisms decay and fossilize, dictates that the planet is exceptionally efficient at erasing biological data. Bacteria, fungi, and chemical oxidation systematically dismantle complex organic molecules, relentlessly returning them to the planetary baseline. But the mammoth lineage managed to bypass this fundamental ecological law. In the extremely high northern latitudes of Siberia and Alaska, the lithosphere acts as an eternal biological vault, a geological phenomenon known as permafrost. Permafrost is not simply frozen topsoil, it is a permanent thermodynamic trap, a matrix of earth, sediment, and ice, where temperatures have remained continuously below the freezing point of water for tens and sometimes hundreds of thousands of years. When a mammoth succumbed to exhaustion in a freezing mudslide or sank into a cryogenic bog, it underwent a geological process that rivals the most advanced modern laboratory cryopreservation. The sudden, extreme drop in temperature immediately halted autolysis, the destructive process where an organism's own cellular enzymes begin to digest its body from the inside out the moment the heart stops beating. More importantly, sinking into the dense, freezing mud created a strictly anoxic or oxygen-free environment. Without atmospheric oxygen, the aggressive aerobic bacteria that drive standard biological decomposition were completely neutralized. Over millennia, the surrounding deep cold slowly drew the remaining moisture out of the tissues through sublimation, essentially freeze-drying the mammoth in deep time. Furthermore, the cell membranes of the mammoth, constructed of specialized lipids naturally engineered to resist extreme cold during life, inadvertently made their tissues incredibly resilient to the mechanical damage of ice crystal formation after death. This specific geological anomaly has yielded biological specimens that completely shatter the standard limitations of the fossil record. When taphonomists recovered Luba, a 1-month-old woolly mammoth calf from the Yamal Peninsula, they did not find a scattered assemblage of bones. They found fully intact skin, heavily muscled tissue, internal organs, and even the remnants of her mother's milk suspended in her stomach. The taphonomic preservation was so pristine that scientists detected microscopic deposits of vivianite, a rare blue iron phosphate mineral, forming deep within her tissues as the phosphate from her slowly degrading bones reacted with iron in the surrounding anoxic clay. In other juvenile specimens, researchers have successfully extracted intact brain folds and networks of blood vessels. By analyzing the botanical fragments of partially digested pollen and seeds trapped in their frozen intestinal tracts, paleobotanists can determine the precise season and sometimes the exact week the animal died over 40,000 years ago. But this incredible preservation introduces a profound scientific paradox known as taphonomic bias. The permafrost only captures and preserves the mammoths that died in highly specific, catastrophic ways. Those that fell into deep ravines, became trapped in collapsing sinkholes, or drowned in glacial lakes. The millions of dominant, successful mammoths that died of old age on the open steppe were rapidly scavenged by direwolves and cave lions, their bones scattered and dissolved by the elements. We are effectively reconstructing a 5 million year dynasty by analyzing only the individuals who experienced the absolute worst possible luck. It is akin to attempting to understand the entirety of modern human civilization by strictly examining the victims of volcanic eruptions. And exactly here, this taphonomic mechanism connects directly to the search for extraterrestrial life and the architecture of the Great Filter. When astrobiologists design robotic rovers to probe the frozen polar caps of Mars or the subsurface ice oceans of Europa and Enceladus, they are relying entirely on the exact taphonomic physics of the Siberian permafrost. If a complex biosphere ever existed on those distant frozen worlds, its biological data will not be found in active surface chemistry. It will be cryogenically locked in the alien permafrost. The mammoth proves that deep cold can act as a universal pause button for biological entropy, preserving the highly complex molecular architecture of life across vast geological timescales. Finding an intact alien equivalent to a mammoth in the Martian ice would instantly answer whether the genesis of life is a universal imperative or a statistical anomaly. However, this ancient biological hard drive on Earth is currently undergoing a violent, planetary-scale corruption. As the modern global climate warms, the Arctic permafrost is rapidly degrading, causing the thermal barrier to fail. As the ice melts, the taphonomic pause button is violently released. Bacteria that have been dormant in the soil for 40,000 years are suddenly waking up and aggressively metabolizing millions of tons of pristine, thawing Pleistocene biomass. This rapid decomposition is venting catastrophic volumes of methane and carbon dioxide back into the modern atmosphere, triggering a massive positive feedback loop that further accelerates global warming. But the issue extends far beyond atmospheric chemistry. It is actively rewriting modern geopolitical economics. The thawing permafrost is physically ejecting the Pleistocene epoch into the 21st century. Across the Siberian tundra, the melting ice is exposing vast, shifting graveyards of mammoth tusks, triggering a massive, unregulated, modern ivory rush. Because the international trade in modern elephant ivory is heavily restricted to prevent poaching, the perfectly preserved taphonomic remnants of the woolly mammoth have become a highly lucrative, legally ambiguous global commodity. We are witnessing an unprecedented, surreal collision between deep geological time and modern human commerce. The taphonomic vault of the permafrost is not just a scientific window into a dead past. It is actively shaping the economic and atmospheric future of our planet, proving that the biological legacy of the mammoth is far from silent. The physical preservation of the mammoth within the Siberian permafrost provides unparalleled anatomical data. But the true frontier of modern paleontology lies deep within the nucleus of its cells. Extracting and reading ancient genetic material is not a simple process of biological recovery. It is a highly complex, computational war against the second law of thermodynamics. To understand the limits of paleogenetics, we must first understand the fundamental fragility of the biological code. Deoxyribonucleic acid is an incredibly dense information storage medium, but it is chemically unstable outside of a living, metabolizing organism. The moment a mammoth died, its cellular repair mechanisms ceased functioning, and entropy immediately took absolute control of its biological architecture. The degradation of ancient DNA is driven by two relentless chemical processes. The first is hydrolysis, where surrounding water molecules physically attack the sugar phosphate backbone of the DNA strand, snapping the long, elegant double helix into millions of microscopic, disconnected fragments. The second process is deamination, a spontaneous chemical reaction that actively rewrites the genetic data. In a deceased organism, cytosine, one of the four fundamental letters of the genetic code, begins to shed an amino group, transforming into uracil. When paleogeneticists attempt to read this degraded code, the sequencing machines interpret this uracil as thymine. The universe is not simply shredding the mammoth's biological blueprint. It is actively introducing millions of typographical errors, scrambling the instructions of life into molecular static. To bypass this thermodynamic erasure, scientists rely on advanced, next-generation sequencing and immense computational power. They extract billions of these shattered, mutated fragments and process them through advanced bioinformatics algorithms. Because the algorithms understand the predictable mathematical rate of deamination, they can digitally reverse the chemical damage, restoring the original letters of the code. Then, using the intact genome of the modern Asian elephant as a biological scaffold, supercomputers map the overlapping mammoth fragments, painfully stitching the massive 3 billion base pair genome back together. But the issue does not stop at simple genomic assembly. The physical limitations of DNA degradation introduce a hard mathematical boundary to our understanding of deep time. Even encased in the absolute ideal conditions of the Siberian deep freeze, DNA possesses a strict biological half-life. Current biochemical models dictate that after approximately 1.5 million years, the genetic fragmentation becomes so severe that no computational power on Earth can reconstruct the sequence. This completely shatters the popular science fiction concept of cloning dinosaurs from the Mesozoic era, which ended over 65 million years ago. Biology has an expiration date, and the fossilization of bone does not stop the ticking clock of molecular decay. And exactly here, this chemical constraint connects directly to the search for life in the universe. If we ever discover the frozen remnants of an extinct biosphere on the icy moons of Jupiter or Saturn, we will be fighting this exact same thermodynamic horizon. The fragility of the genetic molecule implies that the cosmos has a strict, localized memory limit. If a planetary civilization falls to the Great Filter, the universe will ruthlessly wipe its biological hard drive clean in a matter of a few million years. It suggests that biological data is an inherently ephemeral phenomenon, forcing astrobiologists to rely on chemical isotopes and geological anomalies to detect deep-time civilizations. Because the fundamental code of life simply cannot endure the sheer weight of geological time. However, for the mammoth, which exists well within this biological time horizon, the reconstructed genome ceases to be a static map and transforms into an active temporal instrument. This brings us to the profound application of the molecular clock. Throughout the lifespan of any biological lineage, genetic mutations occur at a relatively constant, mathematically predictable rate. While natural selection aggressively purges mutations that alter an animal's physical survival, millions of neutral mutations accumulate silently in the non-coding regions of the DNA. These silent mutations act as the ticking second hand of evolutionary time. By aligning the fully sequenced genome of a woolly mammoth, a Columbian mammoth, and a modern Asian elephant, geneticists can simply count the exact number of microscopic discrepancies between their codes. By applying the known mutation rate, this molecular clock bypasses the physical fossil record entirely, providing an exact mathematical calculation of when these lineages diverged from a common ancestor. It is a biological chronometer that operates entirely independent of the geological strata. The implications of this molecular clock fundamentally alter how we view planetary history. It was this exact mechanism that proved the woolly and Columbian mammoths were continuously interbreeding across the North American continent, mapping their genetic exchange with terrifying precision. It allowed scientists to date the exact millennia when the final populations were severed from the mainland and trapped on Wrangel Island, tracking their catastrophic genetic bottleneck down to the individual accumulated errors. If this mechanism holds true for all carbon-based biology, it means that the evolutionary history of a planet is continuously recorded in the blood of its survivors. Every living organism, including humanity, is carrying a silent, ticking temporal log of ancient population crashes, planetary migrations, and geographic isolation. The molecular clock proves that complex life is the ultimate high-fidelity biological recording medium, an organic ledger that continuously measures the vastness of deep time through the steady, unavoidable accumulation of microscopic errors, right up until the moment the biological engine stops and entropy finally claims the code. The successful sequencing of the mammoth genome did not merely close a paleontological cold case, it opened the door to the most controversial frontier in modern biology, the science of de-extinction. This is not the realm of cinematic science fiction. It is the active, heavily funded application of CRISPR-Cas9, a revolutionary genomic editing technology that functions as highly precise molecular scissors. But the scientific reality of this endeavor requires a strict, objective clarification of what is actually being built in the laboratory. We are not resurrecting the woolly mammoth. Once the absolute genetic lineage was severed on Wrangel Island, the original species was permanently lost to the entropy of the universe. Instead, geneticists are attempting a massive biological patch. They are taking the living genome of the Asian elephant, the mammoth's closest surviving relative, and systematically splicing in the specific extinct alleles responsible for cold adaptation. They are targeting the precise genetic coordinates for brown fat production, oxygen-efficient hemoglobin, and dense guard hairs. The resulting organism will not be a true mammoth. It will be a transgenic proxy, a completely novel synthetic organism engineered to survive in sub-zero environments. But the issue does not stop at simple genetic curiosity. This leads to a deeper consequence regarding planetary engineering. The fundamental purpose of building this synthetic mega-herbivore is not to populate a frozen zoo, but to deploy a highly specialized, self-replicating terraforming tool. This brings us to Pleistocene Park, an ongoing, radical ecological experiment located in the remote reaches of northeastern Siberia. Here, researchers are operating under a bold thermodynamic hypothesis that the rapid thawing of the Arctic permafrost, which threatens to release catastrophic volumes of trapped methane and carbon dioxide, can be artificially halted by restoring the massive biological engines of the past. Currently, by using modern ecological stand-ins like bison, wild horses and reindeer, the project is attempting to mechanically recreate the lost Mammoth Steppe. The preliminary data is staggering. By simply reintroducing heavy herbivores to continuously trample the insulating winter snowpack and violently uproot dark, heat-absorbing shrubs, the winter soil temperatures within the park are registering significantly colder than the ungrazed tundra outside its fences. The animals are actively refrigerating the ground. Furthermore, their grazing promotes the return of pale, high-albedo steppe grasses that reflect summer solar radiation back into space. If a transgenic proxy of the mammoth were introduced into this system, its immense physical mass and biomechanical force would exponentially scale this refrigeration process. They would act as living biological heat sinks, systematically forcing the permafrost back into a frozen state and locking away millions of tons of deadly greenhouse gases. And exactly here, this ecological model connects directly to the search for civilizational longevity and the mechanics of the Great Filter. For thousands of years, humanity has utilized technology almost exclusively to extract energy and dismantle natural biospheres. The de-extinction effort represents a profound planetary paradigm shift, utilizing apex technology to synthetically rebuild the load-bearing pillars of a collapsing global ecosystem. If a technological civilization is to survive its own industrial adolescence, it must inevitably transition from being a planetary consumer to a planetary engineer. The ability to read, edit, and deploy biological software to manually stabilize a destabilizing climate is the ultimate survival test for any advanced species. If we can master this, it suggests that successful civilizations across the cosmos might not survive by building massive, artificial stellar megastructures, but by perfectly integrating their technology back into the deep biology of their home worlds. However, this frontier is fraught with severe scientific and ethical debate. Critics argue that introducing a synthetic, genetically modified mega-herbivore into the modern Arctic constitutes the deliberate release of an alien invasive species. The perfectly balanced ecological network of the Pleistocene is gone. The modern tundra is a vastly different thermodynamic and botanical reality. There is a profound risk that these engineered proxies could trigger unforeseen ecological cascades, violently disrupting the fragile survival of current Arctic fauna. Furthermore, there is the brutal economic paradox of modern conservation. While immense capital and computational power are poured into resurrecting a ghost of the Ice Age, thousands of currently living, vital keystone species are quietly slipping into irreversible extinction. It forces a stark calculation of our scientific priorities. Do we fund the synthetic resurrection of the past or the desperate preservation of the present? Ultimately, the scientific legacy of the mammoth extends far beyond its physical remains locked in the permafrost. For 5 million years, they were the undisputed architects of the Northern Hemisphere, a biological empire that dictated the climate, the geology, and the evolutionary path of our own Paleolithic ancestors. They were perfectly engineered thermodynamic fortresses, yet their utter collapse demonstrates the terrifying fragility of extreme biological specialization in a chaotic universe. They teach us that no matter how physically dominant a species becomes, it remains entirely subservient to the shifting orbital mechanics and hydrological engines of its host planet. As modern humans look toward a rapidly changing global climate, the mammoth stands not as a mythological beast, but as an absolute physical warning. Their silent end on a remote Arctic island is a permanent, undeniable reminder that the universe does not reward past success. Survival is a continuous, unforgiving negotiation with the physical limits of the planet. And the moment a species forgets its place within that delicate thermodynamic system, the ice or the heat will simply reclaim the Earth.